Hello. Sometimes it's of interest to know where invariant points are from our matrix transformations. I'm going to have a look at the three standard ones for sort of linear transformations that we know: stretches, rotations, and reflections. And well, unsurprisingly, going to find the origin is the main invariant point. So how do we do these calculations? Well, let's just remember, if I take an object, I'm going to call that my vector x, I apply the matrix to it, I get an image. And if that point is going to be invariant, it means that my initial point must, its image must be on top of it. Yeah, it must be at the same place. Therefore, m times x must equal x, yeah? And if I was looking at that, opening up the matrix, generalized matrix, A, B, C, D, multiplied by the vector xy, must equal xy. Two ways of solving this. One is simultaneous equations. One is a rearrange and think about the determinant. So let's have a quick look at the latter here. If this is going to be true up here, then I could subtract this vector from both sides. It would have the effect of moving the vector in and adjusting my matrix. So here I'd get A subtract 1, here I get D subtract 1. So that means I've got slightly different matrix. That's the one there. And of course, if it's going to equal 0 on the right hand side, then the determinant of my revised matrix must equal 0. So those are your two approaches. Okay, let's have a quick look. Stretch matrix. Well, stretch in the x direction, stretch factor in the y direction. The matrix operating on x must equal x, therefore that line must be true. Matrix times x was to equal x vector. If I treat this as simultaneous equations, well, my top line is left hand side is just s f x times x, and that must equal x. Well, that's true if x equals 0, or if the scale factor is 1. It's a special case, isn't it? And if I looked at the second line here, that's going to tell me s of fy, that's that there, times y must equal y. There we go. So either y equals 0 or the scale factor in that direction is 1. Okay, so what's that tell us? Well, it tells us that the central point, the origin, is always an invariant point, yeah? But we also have these special cases. The first one is the scale factor in the x direction is 1. Then actually we get an invariant. All the points on this line are invariant. Yeah, it's a line there, isn't it? And similarly, if I said the scale factor in the y direction was 1, therefore every point on this line would stay where it is. So that will be the second invariant line. And of course, in the most trivial case is that both scale factors are 1, in which case every point stays where it is, doesn't it? That's a real special case. Yeah, so what a surprise. The only one that's guaranteed to be is the origin. What about rotations? I think we probably already guessed what we're going to find here, that the only point that's invariant necessarily all the time is the origin. But let's work it through. Here's the equation written. So I've got the matrix operating on vector xy, comes back to xy. That creates two simultaneous equations for the upper and lower lines. If I rearrange that, I can make y the subject. I've got these two expressions here, and I can equate those because they both got to be equal y. What happens then? I can factorize it, and I get this. And I've got a choice then. If that's going to equal 0, well, either x equals 0 or the bracket equals 0. And let's follow through the bracket. If we rearrange the bracket and we carry on using identities here, we are lucky enough that we get down to cos must equal 1. When does cos equal 1? When theta is 0 or 360. Well, they're the trivial rotations, aren't they? Because that's basically saying it's either rotating no distance, so that point stays where it is, or it's rotating 360 and it comes back to where it is. So that's a special case, isn't it, for what we need to do. And that's basically all we want to do with rotations, other than we could follow the same thing down, and rather than eliminating x, we can eliminate, sorry, yeah, we can eliminate x rather than y, and we'd find that y equals 0 is also an invariant point. What a surprise. What's that telling us? Well, of course, it's just telling us that if x equals 0 and y equals 0, that our invariant point is there at the center. Yeah, and our origin is always an invariant point. And the other one are the trivial rotations, where we're either rotating by 0 or 360, in which case all points are invariant. Next one, reflections. Well, I can do the same sort of thing here. Here's my equation. My matrix times my vector must equal my vector. If I write that as two sim equations, I can rearrange them, get y in terms of x, and also cos 2 phi. That's the angle. The phi is the angle of the mirror line. Yeah. So what happens here? I could rearrange it to this equation here. Well, if that's going to be 0, then either x is 0 or the bracket is 0. And we can prove something about the bracket in a minute. So let's have a look at what's happening with the bracket. And we're going to do that by just looking at this first line. Now, that was our upper line of our matrix here. There's our upper line of our matrix written there. And we only need to look at this one. Same's also going to be true of the second line. I'm not going to spend time on it. I had y equals that. And here's an expression in 2 phi. Now, if we look at the top here, 2 phi, I can substitute in my double angle formula. I can substitute in my double angle formula for the lower, for the denominator. What do I get on the top? Well, I've got 1 minus cos squared plus sine squared. Well, 1 minus cos squared is sine squared, isn't it? So I've basically got 2 sine squared on the top, and I've got 2 sine cos on the bottom. What happens? Well, I can start cancelling, and I cancel. What do I get left with? I get y equals x sine over cos, which is y equals tan phi x. What's that telling us? Well, that's telling us that every point on the mirror line is an invariant point. Yeah, that makes sense, doesn't it? Because they don't move. Yeah, so every point on the mirror line, because that angle is going to be phi, and therefore the gradient m is going to be tan phi, isn't it? Okay, so what's that tell us? Well, once again, it tells us that 0, 0 is an invariant point, but it also tells us that every point on the mirror line is an invariant point. Okay, so there we have it in summary. For these 2 by 2 matrices, the origin is an invariant point under the main operations. We have the special cases for where the stretches, where scale factors in stretches are 1, and the most extreme, which give it the top 2 give us invariant lines, and the bottom one here gives us the whole of our region is invariant. Similarly, if we do the special case of the rotation is 0 or 360, all points are invariant. And for a reflection, any point on the mirror line is invariant. So there you have it. Best of luck.